All right. Notes today for finding domain and range of functions. So we had so much fun today. We did not quite get finished with this, so I'm just going to go over this and do some of the problems on the back to help you get a feel for finding domain and range of functions. So domain and range. Domain is all about x. On the x-axis does the graph exist? That's the domain. Where on the y-axis does the graph exist? That's the range. You can determine domain and range by graphing. So I'm looking at these two graphs, and I look and I say, where on the x-axis does this graph exist? Well, if I highlight this, for every one of these x's that I've highlighted, the graph exists. For the graph does not exist to the left here of -3. So that tells me my domain. The domain for this root function, which is all about x, the domain is from -3 and including -3, it's filled in there, all the way to infinity. Now if I shift gears and I talk about the range, then I take my highlighter and I look and I highlight the y-axis where the graph exists. Well, it exists at -1 and everywhere above. So my range would be from -1 up to +infinity. Let's do that again. I'm looking at this quadratic function. I'm looking first for domain, so I'm looking at the x-axis, and well, there's an arrow here and an arrow here, and everything else, everything exists. So what the answer is all real numbers. Over here it would have been arrows here and here. Okay, so the domain for this function is all real numbers from -infinity to +infinity. The range, let's look at this. Well, looking at the y-axis, and I see that it exists up here at 3 and everywhere below. So that tells me my range. My range is including 3, +3, including. Now notice it's everything beneath 3. So I put my 3 at the right end of my domain, my range, the right end of my range, and I say from -infinity up to and including 3. The soft brackets, remember, mean do not include this number. Okay? And infinity can never be bound. So it's a beautiful math concept. We can't bind it. Okay, domain. Well, what if we don't have a graph? We just have a function. You can determine the domain by using algebra. There are 2 flags. Okay, so I'm going to draw a flag. Woo. Okay, the first flag is, I'm going to write it in red right here. I'm going to put a 4 here. Even roots. Okay, any even roots change your domain. You have to limit the domain. Okay, that's one flag. Even roots. It could be the 4th root, the square root, the 6th root, whatever root. Okay, second flag. So I'm going to draw a flag. Okay, the second root is when I have x in the denominator. Okay? So in either of these 2 cases, I have to change the domain, because if I have 1 over x, there are cases where the graph does not exist, because if x equals 0, then the graph does not exist. You cannot divide by 0. It is undefined. So in this case, the domain would be all real numbers, but don't include 0. Okay, which means go from -infinity up to 0, don't include it. Unite that piece with don't include 0, but go all the way to +infinity. Let's take one more small example. If I had 1 over x minus 4, where would that graph exist? Well, at 0, if I put a 0 in here, it'll be fine. The graph will exist. But you can see it. I know you're thinking, if x is 4. So the domain for this function is all real numbers except 4. And you would write that from -infinity up to +4, don't include 4, and then 4 to +infinity. Okay, so those are the kind of cases I can't have a 0 in the denominator. Okay, so I'm going to write out the steps of what to do again. So let's look for red flags and then determine how to find the domain. For this function, is there a flag? Is there an even root? No. Is there an x in the denominator? No. So the domain is all real numbers. Okay? I'm looking at this next problem down here. Do I have a flag? Yes. I have an even root. So what do I do? So when you have an even root flag, even root, okay, when you have an even root, that's a flag, and what you do is set everything under the radical sign, okay, that's what I mean there, the radical sign, greater than or equal to 0, and solve for x. Okay? Let's do an example. All right, so I'm going to set 2x plus 4. I bring it out, 2x plus 4. I set it greater than or equal to 0. Okay, now I'm going to solve for x. I subtract 4 from both sides, and I get 2x is greater than or equal to negative 4. All right, I got to divide by positive 2. I divide both sides by positive 2, and I get x is greater than or equal to negative 2. So I have put everything under the radical sign greater than or equal to 0, and I solved it. This is my domain, and I'm going to write it. It's greater than negative 2, but it includes negative 2. So I write negative 2 included, up to positive infinity. And that is my domain. Okay? That's what we do when we have root functions. Now let's do this problem. We have a different flag. All right, so let's write a little line here. When you have an x in the denominator, what do you do? When you have an x in the denominator, set the denominator, I'm just going to write it shorthand, set the denominator not equal to 0, but set it not equal to 0 and solve for x. So here's what I do. All right, look at this problem. Oops, there's a flag. So I take the entire denominator, x plus 2. I set it not equal to 0 because the whole denominator cannot equal 0. That's just true. I'm going to solve for x. Subtract 2 from both sides. X does not equal negative 2. Okay, I'm going to write the domain. So my domain will be go from negative infinity up to negative 2, don't include negative 2. That's part of the domain, united with negative 2 to positive infinity. Okay? All right. So those were the notes for today. Let's do some examples from the back. You can do all these. The answers will be available next class. Let's go to the back and try some. All right. So I have a table and a graph and an equation. Functions are represented generally in one of these three forms. So I want to evaluate combinations of functions. Okay? So this is a new topic. So, I'm sorry, I should have introduced it better. New topic. Whoop. Combinations of functions. New topic. Okay. I want to combine functions. So what I have to do, we talked about this a little bit earlier, we're going to evaluate f at 2, then we'll make a piece, we'll figure that out, then we'll subtract g of 3, and then we'll add h of 2. Okay, so we're going to do these one at a time. So looking here, f at 2, well, f is the table. So what is the function when x is 2? So I go over and say when x is 2, the function y, f of x, right, that is y is 6. So f of 2 is 6. I love tables, they're nice and easy. Don't worry about the minus sign yet, let's just evaluate g at 3. So I look at the function, when x is 3, what is g? Well, g of 3, right here exists is 6. So that's 6. Then I do h at 2. H is an equation, so h of 2, I'm going to have to do some math. I'm going to, when x is 2, I've got to work it out. 3 times 2 squared minus 5 times 2 plus 1. Well, 2 squared is 4, 3 times 4 is 12. Negative 5 times 2 is negative 10 plus 1. 12 and 1 is 13, minus 10 is positive 3. So I evaluate the 3. Now I've evaluated all 3 functions. Now I'm going to combine them. 6 minus 6 is 0, plus 3 is 3. Okay? So if I get this function where it says take h minus f plus g at 1, I could write that another way. That could also be written h at 1 minus f at 1 plus g at 1. And I would do it exactly the way we did it here. Okay, I'm going to do my brackets. Take a bracket. You're going to take one function. You're going to subtract the second function. You're going to add the third function. The brackets will help you keep track of this negative sign, because this can be tricky. So let's do h at 1. H at 1, h is the equation, so I'm going to do h at 1. H at 1 equals 3 times 1 squared minus 5 times 1 plus 1. This is 1 times 3 is 3 minus 5 plus 1. 3 plus 1 is 4. Positive 4 minus 5, negative 1. So h at 1 is negative 1. F at 1. F at 1 is a table. So I look at my table. When x is 1, f of 1 or y is 3. G at 1. I look at the graph. When x is 1, where does the graph exist? It doesn't exist up here, but it does exist down here. So g at 1 is negative 2. Negative 2. So now I have negative 1 minus 3. See, I distribute that negative 1. So negative 1 minus 3 is negative 4. Negative 4 plus another negative 2, the answer is negative 6. Okay, let's do C. C would be 2 times the f at 0. So let's just write the frame of our problem out. I'm going to determine what f at 0 is. Whatever it is, I'm going to multiply it by 2. Then I'm going to subtract, and I'm going to say 3 times whatever g at negative 4 is. So there's the outline of my problem for C. So f at 2. F at 0. So I look at the table. When x is 0, f of x. When x is 0, f of x is negative 4. 2 times negative 4 is negative 8. I'm not worried about the subtraction yet. I'm just worried about g at negative 4. G is the graph. When x is negative 4, the y value of that function, g of x, is positive 5. Okay? Now, I could just say negative 8 minus, I could either multiply this and get negative 3 times 5 is negative 15, or I can say minus 3 times 5, which is positive 15. It's the same thing. There are two negatives added together, and I get negative 23. Just be very careful with laying out the problem so you get your correct sign. This problem D, we're not going to do the whole thing. It's just going to be h at negative 2 times g at negative 2. The negative 2, in a sense, distributes to the h and g. Evaluate each, multiply them together. Let's finding algebraic combinations of functions. This, again, we're going to have to be more careful with our work. What we're going to do is we're going to take f at x plus g at x minus h at x. This is where I definitely like to use my brackets. So f of x is just when I put x in for x, what do I get? Well, f of x is x squared plus 10. This is in brackets. We're going to, there's f. We're going to add that to g of x. Well, what's g of x? It's x, so it's just 4x plus 1, bracket. We're going to subtract, bracket, h of x. Well, h of x is 2x squared plus x minus 6. I'm doing the same thing as I did before, but up above I had a number here, so I input the number. Here it's just an x, so that's what it is. The tricky part here is the negative sign. We have to distribute this negative sign to all three terms. So now I'm going to write everything without brackets. X squared plus 10 plus 4x plus 1. Nothing changes with those. Now I distribute that negative sign. Minus 2x squared. Distribute that minus x, a negative times a negative, plus 6. Now I'm going to combine like terms. First combine your x's. Negative 2x squared and positive 1x squared is negative x squared. I combine my 4x and my negative x to get positive 3x. And then I combine the positive 10, positive 1, and the positive 6. So that's positive 17. Okay? So that is my answer. Right there. Okay? All right, let's do another one. Let's do g of x minus 3 plus f of x. Well, we know how to do f of x. You just write the function. This looks a little harder. Let's do that. So we have g of x. Everywhere there is an x, I'm going to input x minus 3. So I'm working the g of x first. Make your big bracket. G of x plus f of x. Okay? G of x plus f of x. Now we're going to input x minus 3 everywhere there's an x. I'm looking at g of x and I'm saying, okay, I have 4 times, I'm putting in x minus 3 plus 1. Okay? Now, still in the brackets, I'm still working through this piece, I have to distribute the 4. 4x minus 12 plus 1. Still working it. These two can combine to be 4x minus 11. So I've figured out g of x minus 3. Now let's figure out f of x. Well, f of x is just x squared, so it's just x squared. So it's 4x minus 11 plus x squared. Now I have to combine all these three terms, which is really just rewriting them in good order. It's x squared plus 4x minus 11. I always like to write my functions from largest degree to smallest degree. Okay. The next one, number 3. This really is f of x times g